Good morning, all. Glad to be here in front of all of you. I'll start by introducing myself. I'm Kaushik from Accenture. At Accenture, I lead I'm called the Global Asset Engineering Lead. Basically, I'm responsible for all our software asset development and tools and automation that we take to our clients. I've over 20 years in the firm, and over the last 10 years, I've been specializing in the area of applying AI and automation in software development, applications, and platform management. Over the last, I think, 10 years, I'm happy to say I filed over 115 patents in this space. So this is what I do. I am glad to have here with me my long-term collaborator over the last 10 years, Luke. Luke, you want to quickly introduce yourself as well?
Yeah, hi everybody. Luke Higgins. I'm the chief architect responsible for Accenture's global asset and automation deployment. I also work with Kaushik, aka the Wizard, to build out the different capabilities, particularly around the AI ops stack, but also have been contributing in some of the other areas that we'll talk about today. I don't have quite as many patents as Kaushik. I think I'm only about 21. But the last couple of years, or this year, we won the Accenture's Innovation of the Year around some of the work that we've been infusing, and which we'll explain today around how we're using generative AI and some of our AI models. So particularly in the service delivery lifecycle approach, as well as how we enable it in our modern operations. Thanks.
So he called me the Wizard. I call him Tony Stark. So a bit of background, right? So what we are going to talk about is how we bring Gen AI to power innovation across all things technology, right? Software development, application management, migration, modernization, rationalization of software, managing applications and platforms, and how we do this powered by AWS services, specifically Q and the foundation models from AWS. So a little bit of context on how we actually got there. So 2 years back, so we were in the world of automation, AI, and we thought we were onto the next big thing called, you would have heard of it, pair programming. It looked really great. And then suddenly, I think about exactly 2 years back, OpenAI happened. ChatGPT went live and all of that. And suddenly the whole discussion was, okay, do we need people? Do we need software engineers? So there were those who felt everything's going to go away. And then there are many who are very skeptical, including me, on whether any of this is really going to work in a real production system. So being Accenture, what we did is we put a method to it. So the first thing we did is we worked with Stanford to create a scientific model on how we will actually approach applying generative AI in all things, we call it the technology delivery lifecycle, which is all things related to technology, right? So where we actually put a methodology to it. And then we had the benefit of, doing over data with over 50,000 projects, all kinds of projects, right? Managing applications, SAP implementations, Oracle implementations, cloud migration projects of different kinds, right? Custom development and so on. So for each of these archetypes, we actually looked at where we have applied automation in the past. We've been doing this for over 20 years, right? We know what works well when it comes to traditional automation when you apply AI. And we created a hypothesis on where we should be applying generative AI. So for example, test automation already worked very well. Ticket automation worked very well. But then what we could never do is do a meaningful root cause analysis of what exactly happened when a ticket was there. We couldn't create designs, for example, or generate code. So those were some of the areas we looked at. What we then did is, so we are primarily a services company, and we have a number of partners like AWS, right? So we spend time with AWS to understand, for example, what AWS is doing in this space around foundation models. Back then, it was Code Whisperer, which AWS is coming up with. So we understood what their AWS's roadmap is, and then looked at how we can complement this, because we run projects, and AWS complements us with capabilities around code generation, testing, the foundation models, etc., which is the third piece, which is create or build by strategy. We then took around 70 what we call as controlled pilots. What it means is we took a project, ran them the usual way, and then created a parallel team, made sure the teams don't talk to each other, and started, the new team would then do the GenAI experiments. They would, for example, develop the same software with GenAI, solve the same tickets with GenAI, etc. And then we compared results. We learned from our mistakes. We documented all of this, and then these became our playbooks, our trainings, everything from technical things, legal regulations, costing, all of that, architecting, etc., which we institutionalize. And then what we are now doing is we are already scaling it and applying it in over 1,200 projects today. So every new project, we apply this. So we have two solutions. We have a platform-based solution where we actually have a platform which we will show you, which uses AWS capabilities, like Q, the foundation models, to do this. And we also have a more open source version where we can actually build this with clients. So what have we learned? How are we actually applying this? And this is what we are actually going to show you, right? So the first question that we get asked is generative AI making us more productive? Answer is absolutely yes, it is. So we do see significant additional productivity as compared to traditional automation, which is over and above this, which complements it. But the real promise of generative AI is actually beyond that, right? So what the typical conversation I have is a lot of IT. Is the left side familiar to you? Most CIOs or CTOs I talk to, they say it looks either like this or more ugly or more beautiful, but something like this on the left side. Where the real promise of this is using traditional techniques and tools, adding GenAI, and getting to something like what you see on the right side, which is beautiful, modular systems, clean, without technical debt, with clean integrations, good usage of data, etc. The ability to go from left to right with smaller risks, quicker results, and much more modular way, right? And the way we apply it is, the 7 things that you see on top. The first and most important thing, which is actually a very foundational step, is taking all of the data from your systems and actually digitizing it using generative AI. It means 2 things, right? There is the explicit knowledge that we document. There is knowledge which is in the minds of people who know the applications and systems. And then there are the unknowns, like, for example, what's lying in the code. So a lot of our clients have, mainframe systems written in COBOL, assembler, etc. So what we do is we digitize what's known. We use multimodal models, for example, conduct a session, record a session like this with consent, and digitize this knowledge and synthesize this with all the other knowledge artifacts that are there, and use that to create system understanding documents, standard operating procedures, etc. The more interesting piece to me is then going after code. A lot of the knowledge in the system is actually lying in the code. Using an agentic approach to reverse engineer this code, running agents. So one of the best examples I can think of is assembler. Taking assembler code, reverse engineering this, we've been able to get a 50% accuracy, where you actually get documentation, where you map code to English. I've written assembler 20 years back. I had to debug an assembler system. I thought it's impossible. I've been proven wrong, and and my hypothesis is if you can do assembler, you can do anything, right? You only have the platforms to deal with where it's more configuration based. I'll show you some of that. The second part of it is managing applications and platforms. So here again, right? We've done ticket automation, we've done monitoring, observability. All of that works very well, but what we, for example, couldn't do is, for example, take a voice call. For example, a call being handled in AWS Connect, and convert that to a ticket, combining information from the user and with the knowledge in the system. That's something we couldn't do before. And for example, in a customer call, every minute is valuable, right? So that's something that we've been able to get. The second part, which is which is always like something I would have wished for over the last 20 years, is As you get a ticket, can you do a root cause analysis? Now you can. So you actually use the knowledge base, use the architecture and the configuration of the current system, get the information that's there in the user call and the ticket, synthesize this and point it to what events happened, and explain the events using generative AI. The third and fourth, so I'll do four first, which is once you have the knowledge, everything across the software development lifecycle, writing new features, writing new stories, using generative AI, which is actually what we're doing now with a number of our clients to generate features fast. So usually I say, where does most of the time in a product release go? Many different views, but one of the common ones is defining the right features and stories. And you can speed that up by providing context on what the current functionality is with Gen AI, with the vector stores. One of the very interesting things which I'll show you is architecture as code. What we've been able to do is use architecture objects. This was there even before generative AI, right? The problem with that was it's very hard to read. You cannot read architecture, or even as a practicing architect, I find it very difficult to read an architecture. But one of the things we realized is with Gen AI, you can generate an architecture object reliably. You cannot generate a diagram reliably, which you can actually use in development. So that's something which we do. So to codify everything from a functional architecture, a technical architecture, an application architecture, development, deployment architecture, et cetera, write it as code and use that as a basis to generate new software. Similarly, UI, code generation, and that's where Q comes in to complement, to take over the actual coding itself, the testing of it, et cetera. Similarly, with platforms, SAP, Oracle, Salesforce, Workday, Adobe, et cetera, generate configurations along with customizations of code. But the other key thing that we also do is, one of the very common questions clients ask is, when do I use standard platform features versus when do I use customizations? So reverse engineering the customizations and helping with decisions and insights on when to keep a standard feature versus when to customize is the other thing that we do with platforms. The last three are to me the most promising ones. Especially when we talk about large development and SI, comparing different applications, overlaying that with insights and diagnostics to find out, for example, what's common. Like for example, one of the clients we had 9 versions of reservation systems where each of them came from a different acquisition. So one of the things we had to do was reverse engineer all of them, compare them, find out what's common, what's different, so that we can make a call on which version. And the 9 versions, some were written in C, some were written in COBOL, some were written in Java, some were written in different exotic languages, and you had to make those calls to compare and written. So that's rationalization. Modernization, rewriting software from one tech stack to another, and data engineering. So usually, we lock up people for 3 days, provide food and water, and take them through all of this and train them. But we will show this, we'll show you quick glimpses of this, and we'll take questions as we go through. Before I switch to the demo, how does this actually look like? So this is the architecture of the platform that we have. So, I usually go bottom up. So we use everything from and this is how we do it with AWS, right? Powered by different AWS tools, the Gen AI models from AWS, ranging from everything in Bedrock, Claude, Llama, etc. The traditional AWS services. What we essentially do is create a data fabric, which actually has our knowledge graphs and vector stores that codify everything that we get on the current system. Use an AI layer. So some of the key elements there is what we call as the model switchboard, which means providing the flexibility to pick different models within the same use case, within the same agent, to pick the right model for the right use case or for the right activity. And capabilities like building patterns, having projects and users build their own use cases using the capabilities that the platform has, the knowledge engine, etc. And on that, have all of the different use cases that you see here. And again, the user experience, we either plug it into the tools like Jira, ServiceNow, etc. There is a web interface, there is a chat interface, and then there is an exploration interface where you can try out your own prompts, etc. So I'll pause with slides. I will switch to the, I'll show you a glimpse of it. Oh. No? Okay, so we are on the live platform, which we call GenWizard. So the first thing I'm going to show you is knowledge. How do you actually, get to the knowledge base? So for this, I have here an application from GitHub called Paproc. As you can see here, this is a C-based application written 10 years back, last modified 7 years back. What I'm going to show you is how you actually take this and reverse engineer this using, the entire, suite of foundation models, from Bedrock to get this to simple English functionality, right? So when we started, we didn't know what this actually did. So when we actually take this application in, what you see here is, so here is Paproc loaded into the system. It takes about an hour or so to ingest it, and we do several iterations. The first thing that we do is we have a reverse engineering agent, which will actually go through this. And first, what it does is it actually scans the code, identifies what type of application it is, and gets the best pattern to go about reverse engineering. So here it is calling out a pattern, and we have configured this to pick the AWS stack. So you can see there for every activity, it picks a specific foundation model, a series of trigger prompts to start the whole process, and to go about reverse engineering, right? So, sorry?
Is that defined like which model?
The agent determines it. You can always override it. So what we do up front is we say, look, these are the models I've subscribed to. Pick from this. So, and you can say, I want best possible quality, or I want the lowest cost, highest speed. You can specify those parameters, and the agent will go about picking the right model. Like, for example, to explain assembler, you need the most powerful model available. Similarly, but to explain Terraform, you can pick a smaller model. So those decisions are made. Exactly. Yes. And now once you run this, what you get is something like this. So so I picked a relatively simple application to show you everything. When Luke switches over, we will show you a Java application with 1 million lines of code, how it looks like. And you can relate to some of the Marvel Avengers and DC movies graphics soon when you see it. Okay. So here is the application. So it's, as you can see, it's all C, no pun intended. So let's take one of these, right? So here is the account management. So a lot of C code. Now I can actually take this code and put it straight on a foundation model and try to get an explanation. But the problem with that is you don't know whether what you're getting is right or wrong. And the larger the code, the more difficult it is, right? So what the agent actually does here is it chunks this up. It explains different chunks. But what it also does is the agent will take your explanation in English, convert that back into prompts, regenerate the original code using exactly the same model and exactly the same parameters, and use a deterministic model to compare the two sets of code, not the two sets of explanations, but two sets of code, which is very deterministic. And it scores it. You don't get 90% when you start. You probably get 15, 20% when you're lucky. But then it repeats the chunking, it changes the parameters, changes the model, and keeps redoing this. It keeps redoing this till you get it right. It knows when to stop. If you are stuck, it knows how to call a human friend to get more English. So you're basically reverse engineering a little bit of the human brain to explain what the application does. And then keeps repeating this process till you get a desired score, which you can define here. So you can say, I need 80% accuracy or 70% accuracy, etc. As I do this, I get what you see is a nearly functional explanation like this, which tells you in business terms what the application is doing, and there are the technical references. But with this as a starting point, I can now do a lot of interesting things. So the first thing I can do is take this English explanation and convert this into stories. I can write prompts to say, describe the same code through user stories. So this is telling you in very simple functional terms, this is, if I had written this application today, this is what the stories would have been, right? And what it does is these are the things that we usually don't like getting into details of, right? What is the detailed description? Acceptance criteria almost never gets defined, but you can make the LLM do that, right? So you get all of this. Once you review this and know that this is correct, you can now use stories as a base. I mean, of course, you can abstract features from it. But the more interesting thing is get a first draft of functional test cases that can test the same stories out, because your functional test cases are tied only to the stories, not the actual code itself, right? So I generate this, again, along with descriptions and even test steps, etc. Once I do this, I can then generate test scripts in a language of choice, in this case, Selenium. What you don't get is the data. The data bindings you do later. I've already done it, so that's why you see it here. And you get the scripts for each of this. I do this for the entire application like this, one at a time. So here is the technical view, but the view that I always like, which it used to be a wish list when I started my career, was something like this. A full graph of the entire application. So which tells you, this is the application, these are the features, these are the stories, these are the test cases, scripts, and all the code attachments and tags against this. I told you about rationalization. I can now take this functional map, and I can map this to an enterprise architecture or a process hierarchy. So what I'm doing here is taking a typical banking process hierarchy. It's a payment application, right? And I've been able to map this to the processes and saying, look, it has cash management, virtual accounts management, etc. So you see different processes that are there in this. Oops. And against each of these, I can always drill down and get the corresponding code back. So now this way, what we do is, if there are many versions of payment application, I can always compare it. I can compare, find out what's different, where is the common functionality, etc., which gives me a basis to rationalize. So this is what interests a lot of techies like us. For a business user, what excites them most is a Wikipedia of the application that we generate like this. So here is a description. You've already seen the features and the stories, but then you can actually go in and generate more interesting stuff like the UML diagrams, the sequence diagrams, the API specs, pseudocode, etc., which you then get it out once and have the team maintain it going forward. So for an unknown application, you get the documentation for this. How am I doing on time? Good? Yeah. Okay. So code to English, but more importantly, you're mapping code to, all the functional descriptions, right? Now, the other part, like this is the difficult piece. The other piece is like, how do I actually take what we already know about the application, the known documents, the calls like this, and get it digitized? So what I'm showing you here is, you can take a session like this, have many different recordings, which is what you're seeing here. Now, for each of these sessions, what you're seeing here is like a 1-hour call, which is actually happened here. So we are, again, using a multimodal model to index this standard stuff. Now, what you're seeing on the right is from the video and the associated documents, we are generating documentation of that particular area of functionality. Now, what we can do is, from the synthesized description of this, we now have users go in. I can actually prompt to get the required level of detail from what I've already digitized, use the code base, etc. But one of the biggest challenges that we see in production systems is we don't have enough standard operating procedures or system understanding documents that actually tell you what the application is actually doing. I can now get this generated where I can actually, I'm manually prompting here, but I can also the agent can actually look at what looks like instructions versus, free-flowing information and generate an SOP like this. So I've taken all the text here, and what you are seeing here is a generated standard operating procedure along with a process flow on how I would resolve different types of tickets or service requests in that particular process area. What I can further do, and is go back here, take a standard operating procedure generated like this, get it properly verified, etc. And from here, I can once I confirm, I just basically curate this. And convert this to an automation workflow like this, which is actually telling me this is how I would actually go about resolving every incident related to of a particular type related to the process area. And this then goes to a ticket resolution engine which you plug into ServiceNow. Or Luke will show you our auto ticket resolver, which actually helps you automate straight from the knowledge that we've actually got transitioned. So I just took you through the first of those, the knowledge part, and what you can do with this. Before I hand over, I'll just show you a couple more things and then over to Luke. Having got this, what can we do with this, right? So one, we can make the product owners write features and stories a lot faster. So what you're seeing here is all the different features that you already saw. But if I have to write a new one, all I need to do is select an existing story or an existing functionality and generate new features, new stories, etc., or make it better. I spoke about architecture as code. So what I can also now do is take all of the knowledge that I've reverse engineered and codified and use this to start generating architecture deliverables. So the first, usually this is this is what I usually follow, and you can configure your own. What we now do is say, take all of this and create a functional architecture artifact from here. So here are all the different features that we already reverse engineered. I can now pick a reference architecture for my system. So you would have yours, or you can pick a standard one. Say, here is my standard reference architecture. And I can use this to now generate a new architecture like this. So this takes about 20 seconds. So what you will see here is it attempts to use your reference architecture, take all the features that are reverse engineered, overlay them onto a functional architecture. In the interest of time, I'll probably pause it here, and so you get a functional architecture like this. So what you're really seeing is an architecture object, but since again we don't want to read an architecture object, we are dumbing it down and providing it as a draw or a Visio diagram, which you can edit right here, right? So anything inaccurate, you can modify it, change it to what you want. You can add layers, you can add components, etc., right here, and confirm what the functional architecture is going to be. In the very same way, what you can also do is get an application architecture. So that's what you're seeing here. So I can say I want a 3-tier application with these layers, write a set of prompts, get this, modify, and so this, I then confirm what my application architecture is. One of the other interesting things we can now do is, you saw that the whole application is in C. I want to rewrite the UI. I can say, look, I want a React UI. So it takes the current logic and then you start the process of rewriting it on a new tech stack, which actually tells you how you convert it. Similarly, with every layer. What we then do is use this, specify a technical architecture pattern. I want an event-driven serverless architecture on Lambda, etc. And I get a technical architecture as code like this. And from here, I can actually provision the entire development environment through Ansible Terraform scripts, infrastructure as code. Because I have architecture as code, I can then trigger this whole thing off, and I get the environment provision, and I also test out the architecture to see if it is one of those PowerPoint architectures or a real architecture, which I actually do. And if I promote this into production, that actually becomes my production configuration. Similarly, designs, user interfaces, etc. One of the things that so when we pseudo code, we generate all of that. In each step, very similar to what I showed you. You set an accuracy in each step, and it's not like you run it end to end. Every step you have the human verifying it, it's there to augment. In the world of Gen AI, I say 60 to 70% accuracy is great. Right? And then you need to have the human verify and do the rest of it, right? Once you get the pseudo code, the code related specifications, you can now generate it on the basis of the architecture you saw. Choose a stack like this. So in this case, we are choosing Q, the different components. You create a code branch, and basically you publish it to the repository, and you get a developer IDE with the required plugins, the required code generated, and then they start coding using Q right away. So that's this piece. And similarly for testing, etc., which you've seen. Last piece before I hand over, I'll show you one exciting thing, and then over to Luke, which is the same reverse engineering that you saw, we can now do it right across a stack, where we can take a CMDB, read everything that's there in the CMDB, enrich it with a process hierarchy. So what you then get is you get a CMDB like this, right? Relatively empty. This is how most production systems and configurations really look like, right? With different degrees of accuracy. What we are now able to do is get all of this knowledge ingested, get the documents ingested, and then get the process information and what processes this relates to. And this actually helps us enrich the same CMDB. What you're seeing here is a much more accurate CMDB with most of these populated. With the enriched CMDB, we now do your diagnostics, consumption analytics, etc., overlay all of this, and then take decisions on what to rationalize, what to modernize, how to simplify the IT estate, and then how you start, modernizing or rewriting the systems. And then get recommendations like this on what to do with the applications, what to retire, what to keep, where you have overlapping functionalities, etc. Generate recommendations like this, and then start the whole process of software development. So very quick glimpse on different things that we see here. So this is all the things that we do in terms of setting the knowledge, developing new software, rewriting software, simplifying the stack, etc. Now I'll hand it over to Luke to show some of the magic that you do on the live production system in terms of incidents, monitoring, observability.
Thanks.
And you will see the million lines reverse engineered, which he triggered as well. Yeah. Yep.
Great. So the last 6 months, I've been fortunate enough to be at MIT, working and going through a course at MIT, specifically at figuring out, how we, and our major team's project is figuring out how we actually apply this technology into the enterprise. And they first taught us it's really important for us to understand the problem statement that we're really trying to solve for. And so I created these two views because for me, this is the actual problem on the right that we're facing inside the IT enterprise. And as Kaushik mentioned in his picture, we've layered our systems and encapsulated them. And we've layered them because we needed to get the key features out to market quickly. And in doing so, we layered core legacy systems and then subsequently now we're at a situation where, in many of our larger clients, they're at the core of their systems, there's the core mainframes. And we need to, all these legacy million-line Java applications that are as old as my career and made up of many different iterations of that language, as well as many other permutations. And on the left-hand side, we're seeing, obviously, the executive look at the IT services and not see the outcome that they're investing in. And fundamentally, the opportunity that I see, the generative AI is really unlocking is the ability for us, and what's Kaushik's shown, is to be able to understand what's happening in the left, decompose it, and then be able to enable essentially a rewrite of the system. So
are you rewriting a watermelon?
Yeah. I'll be trying to fix the watermelon to actually make it 100% green. Now, when we look at the service delivery lifecycle, this is what we map out. And you can see on the left-hand side, obviously, is the core monitoring systems. And where we've been infusing AI is into our event ops layers so that it can actually start to enable smarter correlation, but start to use that living knowledge base that Kaushik spoke about. Because we can infuse the core intelligence that comes essentially out of that knowledge base that we've been building out to be able to help us with enabling the RCA. And then from there, we move it through into the right-hand side loop, which is essentially managed by workflow. When we first started this process, we were triggering core pipelines to enable, obviously, change in the environment. We soon realized that we needed to actually use workflow to encapsulate automated scripts, obviously with Ansible or Terraform, but also pipelines as well, and potentially other sorts of automation. And then bring it through the lifecycle to resolution. Now, what we've been working on recently is actually the resolution code generator, because now we can actually start to pass in the information we're getting out of the core events, pass it through triage within the workflow itself, and then pass it into the first step of agents to be able to enable the resolutions to be generated, or at least partially generated. And if nothing else, we can at least first do a code impact assessment. And so when we've been looking at the lifecycle of the SDLC, we're seeing those three core primary use cases. The first, obviously, is the forward engineering, which Kaushik was showing. The second being the reverse engineering. And the third, enabling a CIA, what we call a CIA on top of that reverse engineering to be able to do the code impact assessment on existing code bases that we have reverse engineered. So we can determine, where do we need to make the changes in the code base, and then subsequently what potentially we could be making changes on.
Just to be very clear, CIA is change impact analysis.
Yep, that's right.
And nothing else.
Yeah. Yeah, no, we're not in the CIA yet. So I might just show you briefly that sort of blueprinted architecture, just so you can see kind of how we see it coming together. Now, for us, each of our core assets that we built out around the automation workflow, as well as the event ops layers, we've built out predominantly in core Amazon serverless. In the automation layer, it's actually running on Kubernetes clusters. But when it comes to the event ops layer, it's completely serverless. And we're starting to move to more of a base serverless architecture, and it's running on Amazon serverless in key Amazon component serverless components that we then assemble together and augment. And we're finding that this new architecture is allowing us to have improved resiliency, but fundamentally also the ability for us to scale, as well as, and then we can augment that based architecture as we add in new capabilities and features. So we're seeing as well a huge reduction in the amount of security overheads that traditionally we've had to maintain if we have the larger stack across the organization. Now, if we go back to the SDLC, this is the way that we see that flow working through the reverse engineering into the business requirements through to the app arcs. Some of the interesting learnings that we've had was, and Kaushik mentioned it briefly, but when we first started the reverse engineering, we were really looking at the generative AI to discover the code and understand it. And since then, now what we've essentially incorporated is algorithmic approaches to actually parse out the base code bases and structures, and then we enable what he was demonstrating, which is essentially the code explanations themselves inside that graph, so that we can subsequently then map it through in an organized structure, since we needed that structure to reduce the probabilistic error that otherwise we would be subsequently creating. The results that we're seeing at the moment, and it does range, obviously, depending on the complexity of code base, but we are seeing the improvement of effort by between 30 and 40%, and we're seeing the improvement of speed in a similar fashion, being able to generate, obviously, large chunks of these artifacts. And I think when we first started this journey, we were really concentrating on code generation, but then we immediately realized that the broader SDLC has so many other opportunities, and you actually need to start to look at those other layers and introduce the generative approaches, because the detail that you need to actually have when you actually go to do code generation, and when we're doing code generation, we're obviously generating the first tranches, of the code outcomes, needs to have a lot more information in order to make sure we produce something that is a lot more complete. Now, when we go through to our newer workflows when it comes to SDLC, this is the approach that we're following, and we're starting to work through how we incorporate the agentic networks into our core workflow approaches. And what we're finding is that the ability for us to obviously use the agentic networks to first create the understanding of the code is critical from an actual BA's type role. And off the back of that, what we're generating essentially, and it really depends what we're trying to actually do as far as the outcome. So if we're looking to transform the code base then into a new language, like Kashik was talking about, when we do a reverse engineering, really what we're doing is looking at reverse engineering the behavioral understanding of the code base, because we do not want to include the core application content. So one of our larger clients, we were transforming an older Angular application into React, and when we were doing that process, we reverse engineered initially, including the core application architecture. And of course, when we then subsequently then started to pass that on to the forward engineering agent, it started to create a React application, but it was a bit of a Frankenstein, because fundamentally it was taking into consideration the application architecture of the Angular. And so from there, we started to curate the outcome of the agentic networks to be able to make sure that we just carried through the key functional flows. We have the human in the loop then to understand what they are and curate them. And then from there, we pass it to the secondary agentic networks, which then obviously do the core generation of code. Now, when we assessed the reverse engineering outcomes, we saw that it was remarkably accurate when we did it from code. We were seeing it in the 80s in that particular scenario, which was fantastic. And we knew that because we went through, reviewed it, obviously as humans, to then improve and curate it. And then we passed it subsequently on to the secondary stage. And the CIA, or the transform forward engineering outcome, was about 60% complete. And we knew that because we actually then benchmarked it and completed the code base as well. Now you can see that we have these flows here. So within our workflow engine itself, what we've done is we've incorporated as nodes the particular agentic network steps, and then we're passing it into, as we would normally, into our CI/CD loops. And so off the back of the CI/CD loops, it's passing back into the agentic networks, what isn't working or what's getting thrown out, say for security, SAST and DAST outcomes. And then it gets corrected before it then passes on to the human in the loop. At this part, where we have our Q developer assistants also helping our human in the loop to complete what they're doing, and then again it can pass back through the agentic networks to fix the issues. Now, obviously, we would also do an element of testing in this layer as well, in an automated way, wherever possible, and then eventually the final human in the loop test. We're seeing that we're getting a huge amount of savings, obviously, where we're enabling the agentic network to do the heavy lifting, and we are and parts of obviously that loopback layer where we're being able to fix defects or fix issues that is coming out of the CI/CD. Now, I might just pass it over to my computer, if you can transition it across to just do the demo. That'd be great. Thanks. Now, that first flow that I was showing you, what we're seeing here is our SaaS automation service, which is essentially automating, obviously, many different workflows across the clients that we have on our SaaS. Now, we have our assets deployed in our SaaS cloud in 21 different countries across different regions. But we also have it fundamentally running in clients' premises as well, where they want it to run internally. So you can see over the last couple of weeks, essentially, we've automated somewhere in the vicinity of 5 million different tickets, and the chatbots are involved in that process as well. And essentially, we're working through resolving all the particular issues that come through. Now, one of the examples that Kashik spoke about was the call center example, that we're also infusing that now also into our call centers, so that this flow doesn't just have to receive tickets through the particular ticketing engines. It can also come in through Amazon Connect and the IVR. Now, I made this call a little bit earlier today, just sort of you can see what we found when we started these use cases initially was we saw that our call center teams would be spending quite a lot of time transcribing information into some form of a templated ticket before it would then get lodged in the system. And so initially when we were applying Gen AI, we were applying this core template just to sort of summarize. And you can see here, I gave a particular issue around no longer receiving orders, the time that it began, no known workaround. You can see how nicely the template gets cleaned up. Now, from there, what's actually occurring is that it's obviously getting lodged in our system, and it's starting to flow through that loop that we spoke about, where it gets enriched. And that knowledge engine, or that knowledge base, gets incorporated to be able to then work through, what are the likely issues that are causing the issue, and what the resolution steps are. Now, off the back of this, we're also linking that through our EventOps layer, which is actually doing this enrichment, updating the ticket, and then it's starting to route it into that automation loop, which is then powered through the workflow. And we're finding that we can really cut down by somewhere in the vicinity of like 70 to 80% the time it's taking, so the MTTR, from essentially what was taking for people to actually do that triage. Before that, what we would see is huge conference calls, everyone would be invited, they would then have to deliberate, obviously on the actual issue itself. By being able to do this enrichment, this routing to the particular root cause, and then we're bringing in the right teams, along with the information that the system knows about, we're able to reduce the audience of that call. The automation itself is bringing the teams together. The other benefit is that the information that was shared, by the team on the ground is a lot faster to be encapsulated, and we're not missing information. We're also seeing that would be occurring as well. Now, when it's passing into our EventOps layer, and this is a view of our EventOps, you can see that we look across, all of the key events, and in this particular example, you can see that we start to deduplicate the events down. Now, a lot of the different ticketing systems today are passing, huge volumes of events, into our ticketing systems, but there's a lot of noise. And so what the first job of our EventOps is to really rationalize down the noise by looking at the duplicates, and then start to look for the core master tickets that exist in the system, and then from there look at enabling a form of correlation, across that layer. Now, what we'll be doing is correlating as well against what exists inside the CMDB, and then from there we'll be able to bring it together to be able to see, with the information that we have from obviously the core events in the system, but also the events from the CMDB, exactly what the likely relationships to issues are, as well as then infusing the particular resolution itself that it's pulling out of the knowledge base that we've built. And being able to encapsulate what we saw with our support teams was that they'd be getting spammed with so many different issues. It was very hard for them to determine the relationships between the issues. And then this way we can start to cluster them together, prioritize the master tickets, as well as start to provide the particular resolution itself that it's polling straight out of the data store. Now, as we start to pull this together, you'll also notice the view of problems. And so we're also looking for core pattern sets of problems within the events themselves as well. And some of our larger clients right now are obviously looking for us to be able to eradicate the underlying problems themselves. And so what EventOps is doing is looking for those repeating patterns as well, to determine exactly when certain problems began, and then subsequently, again, using that information from the knowledge base to be able to then associate what the likely resolution of the issue is. Now, when we actually look across the different workflows that we build, you saw in my initial dashboard we had hundreds of different workflows. This is the example of what that workflow looks like. But what we're now incorporating it to do is enabling our forward and reverse engineering components as well to be encapsulated in the workflow. And so each of these nodes here are becoming agentic. So you can see here when we're generating certain code bases, what that's doing essentially is then being able to encapsulate via the workflow that process, then passing it off into your CI/CD loops, like I was showing in that diagram, to be able to then resolve particular issues that essentially get generated. And then from there, we can obviously then loop it back into completion. So maybe I might just pause here to sort of see if there are any questions on what I've spoken about. No? Okay, great. Yeah. So I might just conclude with just a view of one of our larger applications that we've had to do reverse engineering on. This is a million lines of Java code, which essentially we've reverse engineered out and visualized. And you can see here the complexity of some of these larger applications. And so being able to enable the understanding of obviously those core relationships and then filter via the core functional call trees the particular relationships of core functions. From those relationships, we use them as filters through this reverse engineered core graph to then actually understand exactly what is being impacted through the layers of code. So what this more simplistic PaperRock application, you could see how they get mapped. Under the covers, obviously, we're dealing with millions of lines of code across many different large applications, and obviously we have to use more sophisticated structural graph models to be able to understand and then subsequently be able to reverse engineer them. So this is just a view of them so you can actually appreciate some of the complexity that we're having to deal with. So.